So morning we have seen all the basics of elastic as well as plastic analysis. So we have discussed finally the assumptions in the plastic analysis. So that is a bilinear stress strain curve, and plane section remains plane, and stress strain relation is same in both tension and compression. So then we have seen how the material changes from elastic to plastic as we are increasing the load. So the point here you have to notice that uh, so uh, so if we increase the load, the stress block will keep on changing. Okay. Finally, the linear stress block, that will become a rectangular stress block. Okay, and but you should not think a strain diagram. Okay, the strain diagram was linear, so that will be it will remain linear in plastic state also. So why is the strain is linear in plastic state? Because of our assumption. So assumption 2 is saying the plane section before bending remains plane and normal to the neutral axis during bending. So this assumption is valid for both elastic as well as plastic analysis. That is why you have to, because many times the question will be asking the stress diagram for plastic state. So different option will be given like this. So you have to choose this one. And the same question can be asked the strain diagram for the plastic state. This will be given, and this will be given, and this will be given. So many of you will be usually many students will be choosing this is a strain diagram also. They will be thinking the entire section is as reach the yield stress, so the strain also will be it may look like this. So that is actually wrong. The strain diagram will remain the linear. Okay, this will be the case. So that is because of our assumption. That is what our assumption 2 is saying. The plane section has to remain plane even after bending. Okay. So the strain will be linear, but your stress block may change. It will become the rectangular stress block. That is the first point. And second point is, so where is your neutral axis? So where is your neutral axis in the plastic state? So that is a very important concept that we will discuss later on. We will derive also. So this is your final neutral axis. So if you look at the fully plastic section, because this is my plastic section, so I have uniform compressive stress of sigma y above the neutral axis, and below the neutral axis I have uniform tensile stress is equal to sigma y. So there is a layer is there, so means there is no stress. So this is that layer. Okay, or you can say this is your neutral axis in the plastic state. But in the initial stage where your section it was elastic, so that time this was your neutral axis. So for elastic analysis, your neutral axis will be at the centroid, but in the plastic state your neutral axis may shift. So how we are shifting or why it is shifting, we will see later. Okay, so only one point you have to remember: the neutral axis at the elastic state and plastic state is going to be different. There may be a shift between this elastic and plastic state. So this will happen if your section is unsymmetric, and if you have a symmetric section like rectangular section or symmetric I section or circular section, your axis will not shift. But other cases, if you have an unsymmetric section, maybe something like this T section or any unsymmetric section, your elastic neutral axis and plastic neutral axis both will be different. So that we will derive, okay, maybe today itself. Okay, we will see later. But that point you have to notice. That is what we can observe from this the stress changes. So here the zero stress, and slowly gradually your neutral axis is shifting downwards, and finally it is becoming here. Okay, so that we will see later in detail. Okay. Okay, I think up to this we have completed. Okay, up to this we have completed. So let us go see the remaining things. So this is the conclusion we can say at the stage 5. In the stage 5, so we have the section is fully plastic. So fully plastic means your stress will be like this. Above neutral axis I have tensile compressive stress uniform value. Every fiber has reached the yield stress sigma y. So here same thing, tensile stress. So all the fibers have reached the yield stress. But whereas in elastic state, what is the difference? Only the extreme fibers has reached the yield stress. All the remaining fibers, inside fibers will be the stress value will be very much lesser than your yield stress. And so you can find out the moment of resistance corresponding to this state. So you keep on increase the load, and at particular value of load, your the cross section will become fully plastic. It will be in a plastic state, and corresponding moment of resistance we can find out. So that moment of resistance will be calling plastic moment of resistance (MP). And if you are finding out the moment of resistance corresponding to this elastic state linear stress block, you that is you will be calling that is a elastic moment of resistance. So how will you find the moment of resistance? We will discuss that. Okay, so usually if you have the stress block, you can this is my compressive stress. I can find out the compressive force that will be acting at the CG of this stress block, and this is my tensile force. Okay, this is my tensile force. So I can find out the difference between this is my tensile force, it is my compressive force. I can find out the distance between this tensile force and compressive force, and that is known as your lever arm. So I can find out the moment of resistance, that will be My. So that is equal to the compressive force into the lever arm, or tensile force into lever arm. Compressive force equal to tensile force. That we'll discuss later on. Okay. So in the similar way, you can find out the moment of resistance corresponding to plastic state also. Okay, that moment of resistance we will be calling the plastic moment. So how to get the plastic moment we will discuss. Okay. So and in the elastic state, it is much simpler because we can directly use our elastic formula. So I have the equation stress equal to m by I into y. So from here itself I can find out the moment of resistance. You can take this is sigma y. So the moment of resistance, that is a yield moment. Okay, the corresponding moment of resistance in elastic state, that is a my yield moment. Okay, maybe this one we can say yield moment. So yield moment mean only extreme fiber has reached the uh, yield stress. So this one you can find my is equal to sigma y into I by y. So the I by y is nothing but your elastic section modulus. So this equation is valid for elastic state only. So plastic state we have to find the compressive force into lever. So that will do next. Okay. So let just understand what you mean plastic moment of resistance, because the stress flow has changed. So correspondingly the moment of resistance also will be different. So definitely you will be having higher moment of resistance corresponding to this stress flow, because in this state each and every fiber has reached its maximum capacity yield strength, so that it can take much more load compared to this elastic moment. So that we will discuss maybe little more in detail. So the plastic moment of resistance, or simply we'll be calling plastic moment. So this is the it is the let me write it is the moment which it is the moment which generates plastic state. Plastic state at a cross section. So at a cross section, the plastic state means this will be the stress. The stress block will be something like this, rectangular. So if you apply, so the corresponding moment, okay, how much moment you have to apply to reach the plastic state, that is known as plastic moment resistance. Because at any stage, your external moment and the internal moment resistance both will be same. So you can say it both ways. So if you apply, suppose this is the state it has reached, the plastic state, and if you apply any further load, then what is the problem? Then no more resistance uh, in. So then there is no more resistance in the material. There is no more resistance in the material. It will just collapse as per our theory, because all the fibers have reached its maximum, that is a yield strength. So there is no more fibers are remaining to reach the yield strength. So it will just collapse as per our theory. Okay. But actually the sigma u is the ultimate strength, but that is not we are not considering that sigma u in the plastic analysis. So at this state no fibers left to reach yield point, so that is why this is a limiting condition in my analysis. Okay, so now let us take a section, let us take a beam cross section. So maybe I will take a rectangular beam cross section. Let me try to draw a three-dimensional view. This is my beam. Okay, so at the elastic state, what will be the stress diagram at the elastic state? It will be linear. So at this, let us assume sagging moment. Let us assume sagging moment. So at the somewhere here I will be having the total axis. This is my neutral axis in the elastic state. So above the neutral axis I have the compressive stress. So what is the compressive stress? That is actually bending normal stress. Okay, bending stress only. Bending normal stress acting normal to the cross section. So the maximum compressive stress will be acting somewhere here. So I can show like this. I can draw like this. This is the maximum compressive stress acting at the extreme top fiber. So what is the stress at this neutral axis? That will be 0. So in between, what is the variation? There will be linear variation. Let me draw it 3D view, so it will be much more clear. So it is something like this. I think you are getting what I am trying to say. This is the compressive stress acting. So again, it's a bending stress that it is acting normal to the cross section. Okay. So we can see that what will be this angle? This angle will be just 90 degree because it is a normal stress acting perpendicular to the cross section. This is the stresses acting above the neutral axis. So now we can see what is the stress acting below the neutral axis. So at the extreme bottom fiber we will have maximum tensile stress. So it is a tensile stress pin away from your neutral axis. So let me, so uniform, this value is uniform everywhere at a particular level. It will vary linearly. So it may be something like this. So this is how we have to draw the stress block actually, because it is actually perpendicular to the cross section normal stress, no? So we have to draw like this only. So this is the tensile stress. So I think you understood. This angle will be 90 degree. That means that is because the 90 degree, it is because it is a normal stress only. It is 90 degree. Okay, these stresses are nothing but the normal stress. So maybe in the elastic state, the limiting condition, this is the yield compressive stress, it is the yield tensile stress. Okay, so let me write some of the assumption, assuming sagging moment to draw this stress block. So assuming sagging moment. So this 90 degree, because that is the flexural stress. It is nothing but the stresses what I have drawn, that is nothing but the flexural stress. So what is that? It is nothing but your normal stress only. We can say flexural stress is a normal stress only, bending normal stress. So bending. So that is why we are calling it the compression and tension. The compression and tension always it acts perpendicular to that section only. Okay. So this is bending normal stress. So this is the, but usually what you will do, how we are drawing this stress block. Usually what you will draw is, this is an elastic state, elastic. So usually we will not draw the stress block like this. So we will draw the cross section. Let us say it is a rectangular beam. So the beam cross section, this is my total axis. The stress and strain are 0 at that level. So we will draw like this only. So I will draw the stress, bending stress like this always. Okay. So this is my compressive stress and it is my tensile stress. Okay. So it does not be, this is my cross section. So this stress is acting not parallel to the cross section, it is acting normal to the cross section. That is why I have drawn this three-dimensional drawing. But usually we will draw like this only. It does not mean that your stress is acting parallel to the cross section, it is acting perpendicular to the cross section only. Okay, like this. That is what your bending normal stress. Okay, this stress is given by M by Z. Okay. So what will happen in the plastic state? So I will be having the same beam. So let us draw the three-dimensional view. So this is my beam cross section. This is my beam cross section. So rectangular beam. So let me draw here. And okay, and take the neutral axis, plastic neutral axis. Okay, it is a plastic neutral axis. So let us say this is my neutral axis in the plastic state. So this is the plastic state. Okay, and what is the stress variation in the plastic state? Above the neutral axis, I will have compressive stress. Everywhere, all the fibers will have same compressive stress. So this is yield stress. It is also yield stress. So everywhere we have uniform stress value. So this will be something like this. So you can say, yeah, this is my stress block. So I think you can understand what I am trying to draw. This is a entire above the neutralized entire cross section. It is subjected to uniform compressive stress sigma y in the plastic state. So what will happen below the neutral axis? Below the neutral axis we have uniform tensile stress. So let me take a different color. So below the neutral axis it is having, okay, it is changing the color. So this is, let me take, so at the below the neutral axis we have uniform tensile stress. Here we have tensile stress, here also tensile stress, everywhere same. So here also same value but tensile stress. So it will be like this. This is how we can draw the three-dimensional stress block. So what is here? So in the simple 2D drawing, how will you draw this? Everywhere I have sigma y. This is compression, it is tension. Okay. So the 2D cross 2D will be drawing something like this. So I have the cross section. This is my plastic neutral axis, and this is my stress block. So all the section has reached same value. It is my compressive stress and it is my tensile stress. Okay, so only point you have to note down here. So I note. So the neutral axis will be different in elastic and elastic state. Neutral axis. So we will locate the neutral axis. So then it will be clear. Will be different both in elastic state and plastic state, ES and PS. Okay. So now let us find out the what is the moment of resistance. Let us find out what is the plastic moment. That is nothing but the moment of resistance corresponding to this stage. The moment of resistance corresponding to this state of stress is known as plastic moment. So let us find out that. That is the next. The cross section can be anything. Let us take an arbitrary shape only. Let us take an arbitrary shape. So do I have something? Okay. Here a slide is there. Okay, so let us take an arbitrary shape here, and so it is, this is my plastic neutral axis. Okay, so let us assume this cross section of your beam, it has reached the plastic state. So now our job is to find out the corresponding moment of resistance. That is what we will be calling plastic moment of resistance. So let us, so this cross section is already reached in the plastic state. So I can draw the corresponding stress block. So it is a uniform value. Okay, don't mind this. So this is a uniform value. Okay, yeah. So this is sigma y. This is also sigma y. So this is compression. So I will draw like this. This is tension. Let me draw like this. So this is basically below neutral axis tensile stress. This is tension. This is compression. So let us say that this. So this is my neutral axis. Okay, plastic neutral axis. So let me call the area above the neutral axis, that is I am calling A1. Okay, and area below the neutral axis, that is I am calling A2. So okay, let me write here. So A is nothing but the total cross sectional area of your beam. So let me write that is equal to A1 plus A2. And A1, so what is A1? The area under compression. Area under compression. Area under compression. And what is A2? Area under tension. So area of cross section under tension. Okay, so finally, whatever is the state, elastic or plastic or elastoplastic, whatever it is, finally, at any point of time, it should be in equilibrium. The beam, the forces should be in equilibrium. Okay, so by equilibrium condition, I can write. So by equilibrium condition, I can write. So you can just see the this stress block at this cross section. If you see the forces acting at the cross section, so I have the compressive stress and I have the tensile stress. So because of the compressive stress, if you multiply the compressive stress into the area on which that compressive stress acting, okay, if you multiply that compressive stress sigma y, it is a uniform value. If you multiply that stress into corresponding area A1, it is the area under compression, and you will get the compressive force. Similarly, if you multiply the tensile stress and into area, you will get tensile force. So finally, what is the equilibrium condition? Total force, summation of total force, algebraic sum, like total force should be 0. So that means what is your condition? Total compressive force must be equal to total tensile force. So total compressive force, it is equal to total tensile force. So what is total compressive force? Sigma y multiplied with A1, which is equal to total tensile force sigma y into A2. So from here you can say that sigma y is same, so A1 will be equal to A2. So A1 equal to A2. Okay. So that means this is the condition. We can this by using this condition we can locate the neutral axis in the plastic state. Okay. So neutral axis in the this condition may not be satisfied in the elastic state if your section is unsymmetric. That is why if your section is unsymmetric, your elastic and plastic neutral axis location will be different. So whenever the plastic state has been developed, okay, I will write whenever the plastic state developed, the cross section will be divided into two equal parts. The cross section will be divided into two equal parts. So that is what you can say from this A1 equal to A2. The area under compression and area under tension, that will be equal. But elastic neutral axis does not satisfy that condition. Okay. So maybe you can take an example. Suppose if you have a T beam, let us say you have a T beam. So how will you locate the neutral axis, elastic neutral axis? You will find out where is CG. My CG will be close to this. My CG will be somewhere here. This will be my neutral axis in the elastic state. Okay, but there is no condition like this area is under compression. Okay, this area is under tension. So this area and this area of your T beam, that will be different. There is nothing like it should be equal. Okay, so but if you take a symmetric section, for example, if you take a for symmetric sections, for symmetric sections like, so maybe rectangular section or circular section or eye section, symmetric eye sections. So all those sections, what is the uh, where will be your neutral axis? Suppose you have a rectangular section, your neutral axis will be at the centroid or CG. So by automatically this area under compression, okay, and this area under tension, so A1 and A2 will be always equal. Okay, that is why for a symmetric section, so elastic neutral axis and plastic neutral axis will be same. Okay, because this condition already satisfied. For the plastic neutral axis, you have to satisfy this condition. So otherwise it will not be equilibrium because stress is uniform, so area has to be same. Okay, so that is why your elastic and plastic neutral axis will be same for a symmetric section like I section, rectangular section, or square or circular section, etc. But if you have unsymmetric section, the cross section will be plastic and elastic neutral axis will be different. Okay, unsymmetric sections. So many times in GATE exam, the question used to ask, a section will be given, they will ask find out the gap between elastic and plastic neutral axis, something like this. So maybe we'll solve this. There is a gap between elastic and plastic neutral axis, so find out this gap. So usually the question is to come. So what you have to locate the centroid, that is your elastic neutral axis, and you have to locate the plastic neutral axis by using this condition A1 equal to A2. We can just equate area A1 is equal to A2. We can locate where will be this axis. So then we can find out the gap. Okay, that is how you have to solve it. So when a time question is to ask. So, okay, so at plastic section, the cross section will be divided into two equal parts. So if cross section has symmetry, the elastic and plastic neutral axis may coincide. So otherwise may not. Okay, that is the point. So I think it is clear. So now we will see how to derive the plastic moment. Okay, how to derive the plastic moment. So to derive the plastic moment, only we are doing all those things slowly. But each and every points are important. Okay, so a lot of question we have covered already. Subject exam point of. Okay. So now we have to find out the plastic moment. We have to form an expression how to derive the plastic moment. Like we have an expression for yield moment, that is equal to sigma y into zd, elastic section modulus into yield stress will give you the yield moment. So similarly, I have to derive some equation to obtain the plastic moment. But that is what we will be doing. We will do now. So let us take a cross section, arbitrary section. So this is my plastic neutral axis. This is the stress block, the stress distribution at the plastic stage. So the moment is a hogging moment, sagging moment. So of course this will be compressive area under compression. So A1, and this is nothing but your area under tension because the moment is, when I'm just taking the sagging moment, let us say. Okay. So this is the total compressive force, that is sigma y into A1. This is my total tensile force. Okay. So how will you find the moment of how will you find the plastic moment? The plastic moment mb, which is equal to, so how will you find the moment? This is the total compressive force This is the total tensile force. So where this compressive force will be acting? So what we have here, we have a let us say we have a if we have some geometry. Let us say if we have some geometry, and I have an uneven bending, uneven loading. I mean, suppose if you have a yeah. So let us say we have a rectangular beam, and this is my stress block. Let us say we are discussing in the elastic state. Here I will be having compressive force. Here I will be having tensile force. So what? How will you locate? How will you locate the point of action of the compressive force, and how will you locate the point of action of the tensile force? How will you locate that?
Sir, it will be means the lower triangle will be one third from of the height and upper triangle will be third of the
Yeah,
height.
yeah. Okay. So here I have a very regular shape of geometry is very regular. Okay, let us say rectangular section, and the stress is not uniform. The stress is just linearly varying. So this resultant compressive force and resultant tensile force will be acting at the CG of this the stress block. So maybe h by 3 from this height, where h is this height. Okay, so I think you can see that. Okay, so this is my h, and this compressive force will be acting at the CG of this the stress block. Okay, because this cross section is just uniform anyway, so this will be just acting at the CG of your triangular stress block. Okay, but here what is the difference? Here we have let us say I have a the stress block is the stress is just uniform. The stress is just uniform because we are in the plastic state. Okay, so but let us say let us take as a general case, like we have an arbitrary shape. We have some arbitrary shape, the cross section, and so we have already seen that if you multiply this sigma yield stress into the area under compression, you will get the resultant compressive force. And if you multiply the yield stress into area under tension, you will get the tensile force. So here actually we have constant loading, that means constant stress, and uneven geometry. Generally, geometry can be anything. And then where will be this compressive force and tensile force will be acting? Where will act? How will you locate the point of action? So where will be this compressive force will act? Where will be the point of action of the tensile force? So can you tell me that?
Sir, on the same line of action of the force.
So I don't know where is this acting. I don't know because finally I have to find the distance between this compressive force and tensile force so that I can find out the bending moment of resistance. So I don't know where it is acting, where it will act. So I know maybe I know this is H
Distance
or
h by 2 if the height is means the height.
okay, actually that is wrong. So again you have to see this is the first case. I have a regular geometry and the stress is varying. I have an uneven loading. So then result compressive force will be acting as the CG of your stress block, because finally it is not stress block or geometry. Finally what you have to see is the force only, the point of action of the resultant force. Okay, and here I have uneven geometry and I have a constant loading. So the resultant compressive force will be acting at the CG of your cross section. It is going to act at the CG of if you take this area, let us say A1, area under compression, you locate the CG of this area, and at that point only your compressive force will be acting. Okay, because finally you have to see the force only, the stress into area, because here area is uniform. Finally your area is just uniform everywhere, so the area term you can eliminate. You can just concentrate on the CG of the stress block. And here just reverse, the stress is uniform, so okay, you can leave out the stress part. You have to just locate the CG of your area cross section. Okay, so that is why the resultant tensile compressive force, let me write that resultant the compressive force, it is not like always it will act at the CG of a stress block. It is not like that. Okay, it is not like that. We have to see the force that this stress multiply with this much area, that is the force, where that force is going to act. Okay, that is our the question. Okay, the resultant compressive force will act at the CG of the centroid of the compression area A1. Okay, similarly, this tensile force will be acting at the CG of your tensile area, this area below the neutralized. I have this much. Okay, so area, the CG, you locate a CG of your tensile area at that point, that will be the point of action of the tensile force. So now let us say this y1. So now let us say this y1, that is the, you can say, the distance of CG, the distance of CG of, okay, the distance of CG of compression area, distance of CG of compression area from neutral axis. uh, so the neutral axis, I can also say that equal area axis. So I can also call this, the neutral axis at the plastic state is known as equal area axis, because the area above and area below will be equal. So I can also, the equal area axis means the neutral axis at the plastic state. Okay, and similarly, let us say the y2 be the distance of the area under tension from neutral axis. This is called y2 and it is called y1. So now how will you find the plastic moment of resistance? That is nothing but, you have to this, I have a compressive force and I have a tensile force, and definitely by equilibrium your compressive force and tensile force are equal. C is equal to T. So by equilibrium. Okay, and so this will act somewhere here. Let us say this is my resultant force acting at this point CG of your compression area, and I can find out what is the distance between the point of action of the compressive force and the point of action of the tensile force. So this distance I will be calling Z. So let us say that Z is nothing but your the lever arm. So now how will you find the plastic moment of resistance? How will you find the moment of resistance? Can you tell me? How will you find the plastic moment of resistance? So how?
C into lever arm or T into lever arm?
Yeah, either you can take compressive force into lever arm or tensile force into lever arm, because both are equal. So let me write the compressive force into lever arm. Okay, the FC is nothing but the compressive force. Okay, I think I have to write C only, otherwise you may get confused. Okay, so this is your plastic moment of resistance, compressive force into lever arm. Okay, that is equal to, what is the compressive force? That is sigma y into A1, sigma y into A1. What is the lever arm? That is y1 plus y2, y1 plus y2. So what is the value of a1? So we can say that a1 is equal to a2, which is equal to a by 2. So I can take sigma y into a by 2, y1 plus y2. Okay, so maybe I can just rearrange this equation. Plastic moment is equal to sigma y into a by 2 into y1 plus y2. So let us compare this plastic moment equation with elastic moment. So let us compare. So What is the plastic moment? The plastic moment, it is equal to the yield stress into the elastic section modulus. Okay, elastic section modulus. So if you compare these two equations, I can write this plastic moment, it is elastic moment or yield moment, that is equal to the yield stress into elastic section modulus. So I can just write this equation in this form. This term is common, so yield stress into, so I can just take everything as a one term, so I will call that is ZP. Okay, where this is my final equation for the plastic moment, so I can take what is the expression for ZP. So it is equal to A by 2 into y1 plus y2, A by 2 into y1 plus y2. So this is nothing but you can call it as it is called the plastic section modulus. So this is called known as plastic section modulus. So why we are calling plastic section modulus? Just compare it with this equation. This is called the elastic section modulus. Similarly, this term is called plastic section modulus. So this is called elastic section modulus. Okay, so now I got this is like this I can find out the plastic moment capacity of any cross section. You just yield stress into plastic section modulus, and I can find out the plastic section modulus. Just take the area, you can find out area of the given section, y1 bar and y1 and y2, you can find out the CG distance. Then you can simply use this equation. That is called plastic section modulus and plastic moment. So I think it is clear. I think we can see some simple example. Okay, maybe before this we'll see one question like we delete. So is it clear? This any doubt we have this part? It's much simpler. Okay, much very simple. So anybody have any doubt in this?
No, sir.
Okay, so we are going very slow, so we should understand everything. So let me we'll see some questions. Okay, some simple examples. So because we have discussed a lot of things, let us see some few examples. It will be better. The first question, what I was telling, the usually the question used to ask that you find out the gap between elastic and plastic section model neutral axis, something like that. We can take a maybe example one. So I think I don't have the answer. You have to solve it quickly. So let us a T beam is given. A beam is given. T beam cross section is given. It is a T shape. So let us say this is 40 millimeter, and the width of this flange is let us say 100 millimeter. So this is the thickness of your flange is called, it is 40 millimeter. So I think values I have taken uh, because you can directly tell the answer. The values I have taken like that, but every time it will not be like that. Okay, we will see. Okay, this is the cross section. So the question will okay, the question, okay, we have to write a question. Determine. So for the plastic analysis, you can refer any textbook. You can refer the S.K. Duggal also. Okay, that is also very good textbook. S.K. Duggal, design of steel structures by S.K. Duggal. Okay. So I think I have already shared the textbook. You can refer that only for this chapter. I think it will be second chapter of that textbook, the plastic analysis of beams and frame. So that will be a very good, very nice book to read. Okay, for the plastic analysis. So determine the gap between elastic and plastic. Elastic and plastic neutral axis. So elastic neutral axis, you have to give me the answer, because elastic neutral axis is nothing but you have to just locate the centroid. Everybody knows how to locate the centroid. Okay, let us find out everything from a common reference point, that is a top fiber. Let us find out. The first is you have to just find out the elastic neutral axis. Somebody has to solve it. Okay, so that is y bar. So how will you find? Just you have to locate the CG. That is A1. A1 is this area of this part. A1 into y1 bar plus A2 into y2 bar divided by A1 plus A2. A1 plus A2. So which is equal to, what is area? 100 into 40. That is 4000. What is that y1? Y1 bar, that is 20. Okay. And A2, area of this block, 40 into 100, that is 4000 again. So what is the y2 bar? Tell me, what is the y2 bar?
90.
Yeah, 40 plus 50, 90. So centroid, everybody knows how to find the centroid. So divided by area is 4000 plus 4000. So can you give me the answer for this?
55.
It is 65. Okay, okay, just a minute.
55. 55.
Okay, 55.
55.
Okay, okay, just a minute. You just try to solve the plastic neutralizer. Yeah. So so you can directly say the where will be the plastic neutral axis by looking at the geometry. Where will be the plastic neutral axis? In this case, where will be the plastic neutral axis? So what should be the condition? The area above neutral axis and area below neutral axis must be equal. Okay.
At the junction of
Yeah.
flange and wave.
So because this geometry is like this, both are same, so that is why you can directly take this will be the neutral axis. And even if you solve it, you will get same. Okay, the plastic neutral axis, this the distance, I can write distance from. So I think we will take one more example so that you can work out that. Here nothing to do. Directly you can solve. Distance from a top fiber. Okay, top fiber. That means this point. This is a reference to plastic neutral axis. That is directly you can write that will be 40 millimeter. Okay. So now I think can this is the this is my this is the flange. It is my web of your TB. Okay, and this is my plastic neutral axis is somewhere here, because the area is this area of this block and area of this block is same. That is why I can directly say that this will be my plastic neutral axis. So this is the plastic neutral axis. Plastic neutral axis. And where will be the elastic neutral axis? We have already located, that is at a distance of 55 millimeter from top, somewhere here. This is the elastic neutral axis. So this is 55 millimeter and this is 40 millimeter. So we can see this will be the gap. So we can just find out that it is 15 millimeter. So this is the gap. So most of the time, gate exam or they may keep something like this. Geometry may be something like this, so that you can, if you're observing the question correctly, you can save the time to solve it. You don't need to find out. But let us take a different section for just for the practice. So this is much simpler. You don't need to do anything. Okay, just a minute. So I think we'll take. So is it clear this question? Okay, so we'll take another one, the same TB. This means you take say T beam only but different dimensions, so that you can just work out how to locate the plastic node. Like example 2. So I will take a different value. So this is my flange, and this is my, let us say this is my web. So the, let us say the flange width, this time I don't want to keep both are same, I want to keep it different. So let us say this is 1000 millimeter, and this is let us say 40. Okay, and this one, so okay, this I will keep maybe same 1100 millimeter, but width I will keep it less. Width is only 20 millimeter. So now now we will do first plastic, not like elastic. Sorry, the plastic. The elastic you can do elastic, not like this. That is you can do your own. Okay, I don't want to do that, or you can find out if you want. Okay, a1 y1 plus a2 y2 plus a. You can use that a1 y1 plus a2 y2 plus a1 plus a2, and you will get the value. There is nothing to find out. It is Android. So we got this much millimeter, whatever it is. Okay, and how to find the plastic neutral axis? So where will be the plastic neutral axis? It will be in flange, or it will be in web. It is called flange, and this is called web. Flange is much thicker, and web is very, you can say, thinner. So that means this area is more than this area. And then where will be the location of plastic neutral axis? It will be in flange, or it will be in web. Where
The
will,
flange.
yeah, it has to be in flange only, because area above and area below must be equal. So this is the plastic neutral axis. So at some distance from top, let us say this is, maybe we will take this is y1 bar, and this y2 bar. Okay, because you can assume here also, but only thing is you have to do second iteration. So better you don't do like that. You just look at the dimension, and assume the neutral axis accordingly. So I am assuming the neutral axis will be in flange. Okay, so now we can easily solve it. Maybe you can solve your own. Okay, so assume the plastic neutral axis in flange. So how will you find what is the condition at the plastic state or plastic neutral axis? The plastic neutral axis is nothing but, so let me write that definition so that it will be the clear. Plastic neutral axis, it is equal to the equal area axis. Okay, equal area axis. So that means A1 and is equal to A2. So what is A1? Area above the neutral axis. A2, area below the neutral axis. This notation, to understand this notation, I am following this notation only. Okay, everything from this derivation, A1, A2, okay, and Y1, Y2, all the notations are following from here. So that, so what is the A1? A1 is, this is the 100, so I can write 100 into Y, which is equal to, so this is maybe I will take Y, that is better. Let us take only simply Y. So this is 100. 100 into Y, that is equal to, what is this area? Area under tension is this area. So this is the area under tension. This flange plus this web. Okay. So that is nothing but your, can say, this part is 100 into 20. So 20 into 100 plus, so what is this gap? This is 40 minus Y. The total is 40. So this is 40 minus Y. So this is plus 40 minus Y multiply 40 minus Y into 100. So somebody can solve it and give me the value. So this is So I think I have solved it. I have solved 60 by 2, 30 millimeter. Simple. Okay. So this is my the. So this one also you can solve it. So I am not. Let us say it is x. Okay, and your gap that we.
43.33.
Okay, yeah, so 43 point.
33.
Okay, 43.33. Okay, good. So now we can gap between elastic neutral axis and plastic neutral axis. So we can just find out 43.33 minus 30. So 13.33. Simple. Okay, so here this is how we have to locate the plastic neutral axis of any section. It can be I section or it can be any other triangular section. Whatever it is, we have to follow this procedure only. We will assume some here, and then we will write the equation for area A1 and A2. We will just equate. Okay. So I think it is clear. Okay, we will go to the next. So I think it is clear. Anybody have any doubt? Can ask. So here we have seen how to find the plastic moment and the plastic section modulus. So in this slide we got the expression for plastic section modulus, plastic moment. So let us work out some of the standard sections, triangular section or square or rectangular section, circular section, etc. Okay. So let us work out how to find the plastic section modulus, because all these are, it is coming as a question. Okay, everything will be coming as a question. A section will be given, find the plastic section modulus, like that. Okay. So a lot of standard result also you have to remember after that, like moment of inertia we used to remember for a standard geometry, something like that you have to remember for the standard geometry. That will be frequently asked in exams. Okay. So let us take first, let us take a rectangle cross section. So find out the plastic section modulus. Find out the plastic section modulus. How will you find the plastic section modulus? Is that P, that is equal to A by 2 into y1 plus y2. Okay, y1 plus y2, that is the centroid, y1 bar plus y2 bar also you can write. Okay, so let us take, this is the rectangular beam and the width is b and the depth is d. Okay, so the area, it is the plastic section modulus. So for plastic modulus, area is equal to bd. There is nothing, area equal to bd. And where will be the neutral axis? I can directly locate my plastic neutral axis will be at the mid height, at this height. This is by the plastic neutral axis. So I'm just writing PNA, plastic neutral axis. So this is just, you can say it is d by 2. So this is also d by 2. Symmetric section we can directly write always. And what is y1 bar and what is y2 bar? So area under compression, this area. So this is the area under compression. Okay. So you have to find out where will be the CG of this section. Okay, where will be the CG of this section? Let us say somewhere here. And this distance is known as, this is your y1 bar. Okay, and similarly I will be having the CG of your, it is very simple case ultimately. Okay, it is very simple case. So this is the CG of my area under tension and this is your y2 bar. So we can directly write what is the value of y1 bar and y2 bar, that is just d by 2 by 2. So d by 4, d by 4. Okay, so now we can directly find the value of ZP, that is equal to BD, area by 2, BD by 2 into D by 4 plus D by 4. So which is equal to BD by 2 into D by 2. So finally we will get, is it ZP, the plastic section modulus, that is equal to BD square by 4 plus it is your plastic section modulus. Okay. So just for the comparison, you can say what is the elastic section modulus for a rectangular section? What is the elastic section modulus? So what is the elastic section modulus? PD square by
BD square by 6.
6. Yeah. So this is the plus section modulus for a rectangular section. So much very simple. So let us go to the next circular section. So again plastic section modulus. So you can also remember, you have to remember all those very easily. The elastic modulus BD square by 6 and plastic modulus is something higher, BD square by 4. Okay, little higher. Okay, and again ZP that is equal to A by 2 into so y1 bar plus y2 bar. So this is symmetric section. Always the symmetric section. This will be my the plastic neutral axis. Okay, so this is a circular section, and let us say the diameter of this circular section. Let us take this diameter as d. Okay, let's take the diameter is d. So area equal to area of circular section, that is pi by pi r square. Okay, or we can say pi by 4 d square. Pi by 4 d square. So where will be your y1 bar? It is the area under compression, this semicircle. So somewhere here I will have the CG of the semicircle. So CG of semicircle, this will be the y1 bar. Okay, and similarly this is the CG of the semicircle, the tension area. So this is your y2 bar. So can you tell me what is the value y1 bar? Y1 bar equal to how much? The standard
4R by 3 pi.
4r by 3 pi. 4r by 3 pi. So let us write everything in in terms of diameter. So r is equal to d by 2. So 4d by 6 times pi. Okay, 4d by. So now we have to just substitute. All are very simple case. P that is equal to pi by 4 d square, that is area, by 2 multiply plus y1 plus y2. So I am just writing everything. Okay, so because we need practice for the. Okay, so 4d by 6 pi. So this is equal to pi d square by 8 into 4d by 6 pi plus 6 pi. So that will become 4d by 3 pi. Okay, 4d by 3 times pi. So all the pi terms will get cancelled. So the remaining will be how much? D cube 4 by 24. So 1 by 6. D cube by 6. Right? So this is the plastic section modulus. So let us write ZP for a circular section dq by 6. Okay, dq by 6. So I think it is clear. Let us go to the next. So I think it is clear. So let us go. Let us go to the next one. That is the triangular section. It is little lengthy. So I think we will solve it anyway. Okay, so we have to solve it. So let us take a triangular section, and let us take this is a it is a good exercise, bit lengthy, but this one. So this let us take the base is B. Okay, B. Okay, this base is B, and height. Okay, the height is, let us take H. The height is, so first we have to yeah, the equation remains same, is that P that is equal to A by 2 into y1 bar plus y2 bar. So now we have to locate the neutral axis, plastic neutral axis. So the condition is area above and area below it should be same. Okay, that means in this previous two sections your elastic neutral axis and plastic it was same. Okay, it was same, but here it is not going to be same. So let us say my plastic section modulus, sorry, plastic neutral axis, it is there maybe somewhere here. Let us say, so plastic neutral axis, and in the elastic state this neutral axis will be at a height of h by 3. Okay, but in that case this area and this area is not same actually. Okay, that is why we have to work out where it will be. It will not be at h by 3. If it is at h by 3, area above the centroid and area below the centroid, it is not equal. Okay, so at plastic state, at plastic state, what is the condition? A1 must be equal to A2. So anyway, this area you can find out. Area equal to area of this triangle, that is half ph by 2. Okay, and A1 and A2 will be equal. So you can say that. So what you will do is we'll take this is I will assume this is my plastic neutral axis. Okay, and let us say this is B dash. Okay, this is B dash. Okay, and similarly let us say this height is h dash. So now we can write A1, that is A1 equal to half BH. So B dash half BH, B dash H dash by 2. Okay, so what will be this area? That is A1 is going to be half A by 2, right? A1 is equal to A2, which is equal to A by 2. A is the total area, right? A is the total area. So A1 A2 is equal to A by 2. So we can write BH dash by 2, that is equal to BH by 2 by 2. So it is equal to BH by 4. BH by 4. So from here you can so actually we have to form two equations to get the relation between B and B dash and H dash. So B dash H dash, that is equal to what you will get, B dash H dash, that is equal to BH by 2. So you can get this relation from this equation. So maybe let us take this is equation number 1. Let us take this is equation number 1. So now you need one more equation to get the relation between B and B dash and H dash. Okay. So now we can use using the similar triangle. Using the similar triangle. So you can write this B dash by B, that is equal to H dash by H. So B dash by B, which is equal to H dash by H. Okay, B dash by B is equal to H dash by H. Maybe this implies, so B dash you can write B H dash by H. Okay, let us say this is equation number 2. Okay, so from the equation 1, we can get the value of H dash, that is equal to, maybe you can write BH by 2B dash, right? It is just I have just rearranged this equation, so I can write H dash is equal to BH by 2B dash. So now I can substitute. Okay, that is this equation we can substitute in equation number 2. Okay, substitute. So maybe I will just take it as equation 3. No need to give so many equation 1 2 3, but I have just to like this. Okay, substitute equation 3 in equation 2. Okay, substitute equation 3 in equation 2, so you will get, maybe you will get B dash equal to B by H. Okay, so B by H into H dash, will substitute this one, I think. Okay, BH by, So finally what you will get? You will get it is equal to b square by 2 times of b dash. Okay, and now we can from here you can write that b dash equal to b square by 2 b dash. So I can write b dash square. Let us take this b dash into this side. So b dash square equal to b square by 2. So this implies this equation will give you b dash equal to b by root 2. Okay, b by root 2. So similarly now we have equation for h dash. So from equation 3, so the h dash is equal to bh by 2 times b dash. So bh by 2 times b dash equal to b by root 2. So that will give h dash will be equal to h by root 2. So now I got the b dash will be equal to b by root 2, h dash will be equal to h by root 2. So that my a1 and a2 will be equal. Okay, so now we can find out everything. Now I think it is simple. So now we can easily find out the y1 bar and y2 bar. So okay, let us go to the next page. So this is my the cross section. This is b, and okay, this is b dash, h dash, h. So now we have to use this equation. Okay, so p into a by 2 in a by 2 into y1 bar plus y2 bar. So again we have to find the centroid. Okay, the centroid, let us take this is b dash. So the y1 dash will be simple. So this is my centroid of your the compression area. This is the centroid of the compression area. So this is called y1. And similarly the centroid of this trapezoid, you have to locate. That is y2. So y1 we can directly write, I think y1 equal to h dash by 3. This is h dash by 3. H dash is equal to h by root 2 by 3. Okay, I think so h by 3 root 2. It is equal to h by 3 root 2. And how will you find y2? So y2 we can find out. For that maybe you have to use the equation for the trapezoid directly. That will be simple. Suppose we have a trapezoid like this. So let us say this is my trapezoid. Okay, so what is this? This is b dash, this length, and this is b, and what is this height? That is h minus h dash. This is h minus h dash. So then this is my cg, and distance of cg from this b dash. So this distance will be given by direct equation for the trapezoid. Okay, you will be knowing this height by 3, h minus h dash by 3. This you multiply with, if you want to measure the distance from this level, then you have to multiply 2 times this side. So it will be 2b plus 1 into b dash, this b dash by b plus b dash. This is a standard formula you must be knowing. So then again you have to substitute the value of it is going to become a little complicated, like you have to solve it finally, so h minus h dash equal to h by root 2. Okay, h minus h dash root 2. So this one multiply with 2 times b plus b dash, that is b by root 2, plus divided by b plus b dash, that is b by root 2. Okay, so now you know y1 h by 3 root 2, and you know y2 in terms of b and h. h, that is by 2, and you know the area equal to half ph, area of the total triangle, that is half into b into h. So only thing is, now we have to substitute y1, y2 and a in this equation, and then you have to simplify. The simplification will take little bit time. Okay, so you can do in calculator, so it will be, so I'm just giving you the final. So now you substituting, you take everything and substitute back in this equation and then simplify. So basically here you can write maybe something 2 plus 2b plus b by root 2. You can take in a 1 by root 2, that is maybe zero point 0.7. So 2b plus 0.7b, so 2.7. So you can take in decimal form and you can simplify further. Okay. So this is the procedure. I think it is clear. You can just solve it, and this is the value you are going to get finally for the triangular section. 0.09763 bh square. This is the value you will be getting for the triangular section. Okay, so this is just an case. If you have a section like this, you can solve like this. So this is the procedure you can apply for any section. Okay, this is the method you have to apply to find out the plastic section modulus. The plastic section modulus is required to find out the plastic moment. So I think the first part is over. All the basics up to plastic moment, everything is over. So I think we'll start. Okay. Okay, we'll continue. Shall we start?
Yes, sir.
Okay, okay. So okay, we'll continue some more time. So I think we have around 20-25 minutes is remaining. So I think we have understood all those things. All are simple. You just have to practice. Okay. So you just go through that all the theory and just practice it. So yeah. Okay. The next we'll discuss the plastic hinge. The plastic hinge we'll discuss again. Okay. We'll discuss again in detail. It is just give you an idea. Okay. So now we have seen this is the plastic state. Okay, this is the plastic state. This is my cross section, and this is my plastic neutral axis. This is my the stress distribution in the plastic stage. This is known as a plastic state, or you can also call it is a fully plasticized section, because the entire section has reached, each and every fiber in this section has reached the stress level equal to yield stress. You can also call it that is fully yielded zone. Okay, and moment at this stage or moment corresponding to this stage or this stress block, we can call that is the plastic moment. Okay, suppose if you take a structural member, let us say it is a beam or a building frame. So whatever it is, these things are happening at a particular cross section. Okay, so probably where it will happen, if you have a beam, So if you keep on increasing the moment, let us take a simply supported beam, and if you apply some UDL, your maximum moment is where it will be at the midspan. If you keep on increase the load, at which location of your simply supported beam it will reach this plastic state first. At which location? It will be at the midspan, because midspan I have the maximum moment WL square by 8. So at that section only it is going to form the plastic state. uh, it will not form any other section. Okay, okay, so we'll discuss that. And this is happening at a cross section. Okay, this is happening at a particular cross section, and that location of the structural member is called plastic hinge. Okay, that location I can call that is a plastic hinge. So I'm just giving you only that just one line definition. So we will discuss that. Okay, we will discuss that maybe in the coming slide. So let us also I can define the plastic hinge. It is a yielded zone due to flexure in a structure. Okay, you take a structural member. If any cross section has reached this state, then I can call that is a plastic hinge location. Okay, maybe for example, I can take a let us take a simply supported beam. We will discuss that again. Okay, we will discuss this coming in the next slide also. So if you take a simply supported beam, let us say it is a simply supported beam, and apply some loading point load. So of course your moment diagram will be like this. So as we if you keep on increase the load value P, what will happen? It will bend like this, it will bend like this, it will keep on bending, will keep on increasing, and correspondingly it will be initially in the elastic state. Okay, that means initially if you take the mid section, let us take the mid section, mid span. Okay, you take the mid span, and for the initial values of load, your stress block will be in the linear. It will be like this, and you keep on increase the load, and the net effect is your deflection will be keep on increasing in your beam. You can see this deflection will be keep on increasing like this. Okay, and gradually what will happen, your the stress block will become elastic to yield critical stage, then elastoplastic, and finally it will reach fully plastic. This is what happening in the cross section in terms of stress, but this will happen this is the in terms of deflection. The deflection will be keep on increasing as you increase the load, because the deflection at the center will be PLQ by 48A. So finally what will happen is, the moment the structure reaches this stage, that is the fully plasticized section, and that then suddenly will have, it will what till now there was bending, actually till that point there will be bending. Okay, but suddenly when the structure reaches the cross section, this midspan reaches the when it became fully plastic like this, all the fibers has been yielded. Okay, and then suddenly what will happen is, it will that location I can call that is a plastic hinge. This is my plastic hinge. So that location of your beam you can call it a plastic hinge. Okay, and the special the crucial thing about this point is, like, uh, suppose if you have a plastic hinge, what is the moment at that section? The moment will be MB. You will have the moment will be MB plastic moment. But once it formed the plastic hinge at that location, the forming of plastic hinge means the section, all the fibers are yielded. It cannot take any more load beyond that. Okay, so when the structure this cross section has reached, okay, has at this cross section a plastic hinge is formed. Okay, after that if you apply the load, what will happen? It cannot resist any more load. The beam cannot resist any more load, and the load corresponding to this stage of your structure will be calling this is ultimate load or collapse load. Because in this at the plastic hinge, what will happen is, after once the plastic hinge has been formed, it will not resist any further load. If you apply load beyond that point, what will happen? It will just it will act like a hinge only. It will act like your physical hinge. Like the physical hinge mean you have a simply the hinge support. No, you have a hinge support. So what is specialty of this hinge support? It will not have any resistance against rotation. If you apply some moment, it will just rotate. It will keep on rotating. It has no resistance against rotation. The same thing is happening with your plastic hinge also. The once the plastic hinge is formed, that hinge will behave like your physical hinge only. It will not have any resistance against rotation. It will just keep on rotating. Like that means finally what will happen is this it will be just like a, you can say it will be just like a um, the rigid bar. It will just act like a rigid bar. There will not be any bending actually at that stage, because and here I have a mechanic, here I have physical hinge support, and here also I have a hinge support, and here one hinge is forming. It is something like internal hinge, a plastic hinge has formed. So then what is there, I have member something like this. I have three hinge in this member. Okay, so if you apply some load, it will not take any load actually. If you apply some load, what will happen, it will just deform like a rigid body deformation. So that is why it will just act like a rigid bar only. But up to that point there will be bending. These are all the deflector shape. Here we have bending in the beam. Okay, so here we'll have bending in the beam, but the once the plastic hinge has formed in this particular case simply supported beam. So now I have three hinge, two are physical hinge support and one is the plastic hinge. So then it will be just act like a, this will be just a, it will be just straight member. It will be just rigid, it will be just like a rigid bar. So after that, if you apply the load, it will just keep on rotating. It will have it will just rotate about this section only. It will not take any more load. Okay, that is why you can say that the plastic hinge is similar to the physical hinge, and except what is the difference with plastic hinge and plastic hinge and your physical hinge. The difference is at the physical hinge there won't be any moment. The moment will be zero, and it has no resistance against rotation. It is just rotating without any moment of resistance. And except the plastic hinge has, so maybe you can write except your plastic hinge, it is also rotating, but it is having some moment MB. Okay, only that is the difference between the physical hinge and plastic hinge, but it will behave in the similar way. It will not have any more further resistance against rotation. So we will discuss this plastic hinge again. We'll discuss. Okay, so really this point I want to say right now. Okay, then now let us okay, let us discuss. So three stages you can say that, like the if you keep on increase the load, it is having the elastic. Uh, uh, First it is in the linear elastic range, then elastoplastic, then plastic. So basically we can say that there are three stages. The moment of resistance, you can say that three stages. So maybe I will write the moment of resistance. We have discussed already this, but let me write the moment of resistance. Okay, three stages we have, and first stage is elastic stage. The elastic stage. The first stage is elastic stage. So that means this will be the stress block. This may be less than or equal to yield stress. This is the condition. So we can find the corresponding moment of resistance, that will be M. M is, you can say that less than or equal to yield moment. My, that is equal to yield stress into elastic section modulus. That is the first stage. And the next stage will be elastoplastic stage. Elastoplastic stage. That means some part has already yielded and remaining part is not yet reached the yield point. Okay, so this is your stress block may look something like this. Okay, this is my note like this. So this part is already yielded and this part is still in the elastic range. So you can find the corresponding moment of resistance. That moment of resistance will be it will be something more than your yield moment, right? So My, Maybe I will write moment of resistance. That I think that will be better. Moment of resistance. So the moment of resistance corresponding to this stage, that will be more than yield moment. Okay, but it will be less than plastic moment, which is equal to yield strength into plastic section modulus. So that means some fibers has already reached the yield. These fibers already reached the yield. Remaining fibers still in the elastic region. And third stage, that is completely yielded. That is the plastic stage. Okay, plastic stage. That we were stress flow. It's already we are discussed. Okay, I'm just writing all the everything. I'm just writing. Okay, so this is completely yielded sigma y sigma y. So here your moment of resistance, that is going to be moment of resistance, that will be equal to mb. Moment of resistance, that is equal to mb, is equal to yield strength into plastic section modulus. So here every fiber reach the yield strength. Okay, so yes, we have discussed already this. I have just, so in this case utilizes in this stage may shift. In the plastic stage your utilizes may shift. Okay, and that will pass through the equal area axis. Always that will pass through the equal area axis. So now we have to look at at what ultimate load the structure can what is the maximum load the structure can carry. Okay, so that is what we have to do, and that will be known as the plastic analysis of beams and frame. Suppose if you have given a frame or a beam, so you can do a plastic analysis and you can tell that how much load it will take before failure. Okay, how much load it will take before failure. So that will explain with the help of an example.